All right, good morning, everybody. Thank you for joining our webinar today on CLT diaphragms and the Titan plates. My name is Chris. I am the marketing account for Rothoblaas here in North America. I just wanted to remind you all, if you have attended before or if this is your first time attending a webinar, if you do have any questions, we will be answering them at the end of the presentation. If you're on a computer, you can access that from the top bar through the Q&A section, or if you're on a phone, at the bottom right-hand corner, there should be 3 dots, and when that menu pops up, you should also see an option to enter the Q&A section. So without further ado, I'm going to let Alex and Scott introduce themselves and start the presentation.
Got it. Okay. Thank you, Chris. So my name is Alex. I'm one of the technical consultant for Rothoblaas here in the U.S. Um, I've been in the company for about a year and a half now, and uh, done some, handled many consultancies, but also worked on a couple of technical data sheets, and a lot more is a lot coming on its way. So uh, that's me, Scott.
Yes, good morning. Thanks, Alex. I'm Scott Brenneman with Woodworks, where I've been with Woodworks for a little over 12 years now. And I joined Woodworks coming from structural engineering consulting, working in California and the West Coast. And I've had the privilege of really watching mass timber take off in the United States and really help with that. I'm going to be presenting kind of in the middle, so Alex can have things back.
Got it. Thank you, Scott. So let me share my screen. Okay, got it. All right. So, hello everybody. So today we're going to be talking about CLT diaphragms. And so before we get started, I'd like to do a little, I think just a little introduction of who we are. We're what the name say, we're Rothoblaas. We're an international company where we have work in 6 out of 7 continents around the world. But we handle a lot of consultancies. We do a lot of shipments, about 120,000 shipments per year, serving 100 countries. And also we have 25 warehouses scattered around the world. But here in North America, we have three, one in Canada, one in the US, and one in Mexico. But here in the US, I'm currently located right now in Allentown, Pennsylvania, where here at our US headquarters, I deal what about 500 consultancies along with my other colleague Nilu. She's the other tech consultant for the US. So we deal about 500 consultancies. It feels a lot more sometimes, but um, but we were able to serve across 20 states. A lot more is coming along this way, and we have about 1,000 active clients as well. So, and still growing as we talk. So, and wherever you see the gray area, that's where all our staff force is located. So, you can see we're all over North America. So, yeah. So let's get right into it. So COT diaphragms. So what's the reason for COT diaphragms, and why did it came to a point where like we had to consider this? Well, for starters, any building, no matter what structure, no matter the material, has one of the main purposes is to be able to stand up. Structure is not a structure if it cannot handle its own weight or cannot handle any loads. And one load that needs to be able to handle is lateral forces or horizontal forces. And a lot of these horizontal forces are two. You have the wind and earthquakes. And if you want to make sure the building is able to handle wind loads and seismic loads, and the reason for that is because a lot of times, and depending on the region of the country, some of these can be very severe, where you want to make sure a building is able to handle earthquakes with a magnitude of 7 or above, or even 5. Other places where it's not very active it's not an active seismic zone, but it's very windy. And so a lot of times these buildings needs to be able to either be reinforced, or there has to be some sort of connector that's able to resist this type of lateral forces. And for those connected to resist lateral forces, it needs to be able to resist shear forces. But how does lateral forces become shear forces? And so, say for example, you have a wall. So let's say a CLT wall. Um, we don't we, there's you can fabricate CLT walls, but there's a certain length where you can fabricate them. You can only fabricate them in a certain dimensions. So a lot of times people like to like to line up CLT panels and make them and line and connect them with some sort of either like a angle brackets or some other type of connection. And when the lateral force is applied on the wall, it would like to tip over. And when it wants to tip over, one of the angle brackets says no, I want to stay down. And so what ends up happening is crazy shear forces where there's the connection between the walls. And so when it comes to these connectors, it has to be able to resist not just the lateral forces, but the shear forces, and that's where the connectors come into play, and like where the calculations come. Um, but this is just for wall types. What about for floor types? What if like it was like in a 3D perspective? It goes the same as well. Um, Forces are applied not just on an XY direction, but maybe in a Z direction, and so the same principle still applies. Um, you still want to make sure like the floors are able to handle the shear forces as well. Where lateral, such as the wind or seismic, is happening. So there's two type of ways to deal with this. One is the very traditional approach is timber connectors. Um, there's a couple of ways to connect, CLT together. But let's focus on the focus on the two most common ones. You have the spline joints on the spline CLT connector, where you use a spline board and just use nails or fasteners to connect the two. And then the other approach is maybe like a half lap joint, where you make a special cut and just line to be able to overlap each other. Um, this is a great approach, and if done correctly, is able to resist a huge amount of load. However, as you can see, a lot of cuts needs to be made, and if you may not know, that might take that take a lot of precision, and any precision may cost a little bit more money. Not as much as concrete and steel, but it's still something you need to consider. You want to make sure whether or not you want to make these cuts, or maybe you want to there's another use some other sort of connection, and there is. Um, and this is where it leads to the more modern, more mechanical approach, which is just using maybe some custom-made plates, and then using some fasteners to connect the metal plates to the timber. Um, these type of COT connection, or metal spline connections, um, they use usually the best approach is either screws or nails. Sometimes nails are more preferable because it's easy to install. Because with a nail gun, you can just go in and just like connect everything together. Um, and the reason why people like the more modern mechanical approach is because the way the property of steel. Steel is a very ductile material, so it can bend, and it can still resist a bit amount of force. Um, it can handle the seismic, and so when the steel and when that happens, the steel tends to bend first, and we want that. The reason why we want that is because I don't know if you ever snapped a stick or a piece of wood, it snaps, and once it snaps, that's it, it's done. So that's why the mechanical connection has one of the pros, is that it's able to be, easy to replace. You can take out the nails. You can maybe replace it with use a different type of spline connector, and with steel, easy to produce. It doesn't have to be a very thick steel plate. It can be, very sometimes very narrow, easy to manufacture, easy to mass produce, and so not a lot of people like the mechanical connections. Um, and there are some factors you need to consider when it comes to mechanical connections. Uh, One of them being you have to follow one of the new codes being added to for CO2 diaphragm design guides. It's called SPITWITS or SDPWS 2021. In other terms, this is the code for wind and seismic. And from here on, Scott will take it from you, and he'll explain a bit more what SPITWIT is and why is this really important to consider. So, Scott?
Scott, I think we still have you muted.
Yes, thank you, Alex. I'll start sharing my screen. And there we go. And all right, can you confirm you're seeing my intro slide, title slide?
Yes.
Okay, fantastic. All right, well, thank you, Alex. I'm going to go into a little more depth on the CLT diaphragm design using the SPIDWIS, as we call it, which is really like Alex mentioned, our U.S. design standard for designing wind and seismic systems with wood. So that's really kind of special design provisions for wind and seismic. If you're here, you're probably interested in mass timber. These specific webinars are for, I think, for the U.S. market. So this is at Woodworks, we track a lot of the mass timber projects going around the country. And this is a slide that's based on a map we have online that you can go and find using that URL to the bottom right and see the latest of this. But just to track the mass timber projects around the country and how this is, a national phenomenon. And there's really growth of more and more mass timber projects around the country. If you want to browse more information on specific projects, to see pictures of them, who worked on them, we have a different site, which is the Woodworks Innovation Network, where you can, see a lot more information on specific projects. Not every project on this map, but that's another interesting location to really get a feel for what's being done around the country and maybe in your backyard. But there's lots of types of mass timber projects using CLT. From this picture of a hotel being built on an army base during construction, which used CLT floors and CLT walls, to other styles of mass timber building, such as this one, which is an academic building at the University of Massachusetts, where they use CLT floors on a frame of glulam beams and columns. Or other mixtures of framing systems like this apartment complex that's kind of down the road from me here near Spokane, Washington, which use CLT floors over light frame conventional stud walls, as well as mixing materials. So you might have mass timber panels over steel framing or concrete framing. So there's lots of different ways these structural systems come together. But what is common about all the ones I've shown are using CLT floor and roof decks. I'm not going to go into too much into what CLT is, but when you are designing CLT diaphragms, there are some structural properties you need to pay attention to, and maybe some vocabulary about those structural properties that you're not used to, or that can be confusing if you look at the different sources. The first set of structural properties you see from CLT, if you look in, for example, the CLT product standard for the US and North America, including Canada, PRG 320, you see a lot of properties for flatwise panel loading. This is kind of the out-of-plane bending and shear properties of CLT. And those are provided in kind of two strength directions, a major strength direction and a minor strength direction, because CLT is orthotropic with different materials, just like a piece of plywood is. But those are the major strength and minor strength direction and flatwise panel loading. But that's something weird just flipped by. If I go advance now, let's see. Okay. There. Those are properties you can find for the standard grades in PRG 320. And you see that those are the flatwise properties. But when we're doing diaphragm or shear wall design, we also are interested in what the product standard calls edgewise properties. Edgewise is shown in this picture from the PRG 320, where you could see it's like, well, if you took a panel and you put it on edge and supported at the ends, it's kind of like a beam. That's edgewise, but structural engineering term is more like the in-plane properties, the in-plane shear capacity. If you took that edgewise picture and flipped it on side, you can see how this relates to horizontal diaphragms as well. And you're going to be wondering, where do these come from? And what's the terminology? For the edgewise properties, there's many different terms that are used based upon the context. So there's a phrase that you find in the NDS and other places called through the thickness shear. And you can kind of see a picture of that in the top right, where that's kind of like what engineers might call shear in the plane of the panel, in plane shear forces, and then what the PRG 320 calls edgewise shears. They're all the same thing. It's just different context in terms of, is this kind of like a wood structural panel term, shear through the thickness, a structural engineering term, in plane shear forces, or what then PRG 320 calls edgewise. They're all the same thing. And also different sources have different notation for the shear strength. The NDS uses the notation F sub V, T sub V, which is really the shear stress times the thickness of the panel. In the PRG 320 and product reports, you might use a slightly different terminology, F sub VEO, E for edgewise, and 0 and 90 for the major and minor strength directions, and TP being the thickness of the panel versus TV, which is kind of the shear thickness. But even though the notation is slightly different, those are the same terms for the in-plane shear capacity of CLT panels. So where do we get the in-plane shear capacity of CLT panels? You don't find that in the product standard PRG 320, but you will find it in product reports from individual manufacturers. Now, a big caveat is, though, that that's an optional structural property for them to test and publish. So not all CLT product reports in North America include the in-plane shear capacity, but some of them do. If they've gone through that testing to publish those design values for their panels. But one thing to note about these is that they are very strong. In-plane shear capacities, kind of near the middle here is for one manufacturer. We're seeing, values from 5 kips per foot of shear strength to 26 kips per foot of shear strength. And that's at a reference design value. If you were doing ASD wind or seismic design, you get to multiply that by 1.6 over C sub D. So really, the general idea is like these things, the shear capacity in the panels don't really ever control, except in very unusual conditions. But this is how you get the values and where they're from. So yeah, we could have very strong in-plane shear capacity. So taking a step now in terms of where we are in code adoption for our lateral systems and our CLT diaphragm design. If you're familiar with and using a building code based upon the IBC model building code, the 2018 IBC references ASC 716, for our wind and seismic forces. It also references the SPDWS 2015 for the seismic and wind design of wood systems. Now, in SPDWS 2015, we don't have CLT diaphragms and we don't have CLT shear walls, so we didn't have those at that version of this kind of standards. If we move forward now to the IBC 2021, there were some major changes in IBC 2021 where we added the type 4A, 4B, and 4C construction types, which allows mass timber buildings to be built up to 18 stories tall. but as well, there was an update to the there was an update to the version of the SPDWS reference. So their SPDWS was updated with a 2021 edition, and that's now been referenced from the IBC 2021. So this SPDWS 2021 is the first edition of our wood design standards, which covers CLT shear walls and CLT diaphragms. So depending upon where your jurisdictions are on their building code version they're on, you may or may not have this directly referenced in your code to date. But more and more states and jurisdictions are moving to IBC 2021 or even the IBC 2024, which is also available now. So really, for CLT diaphragms, our requirements are coming from the SPDWS 2021, whether or not that is the referenced standard in your jurisdiction at this point. So what's different about SPDWS 2021 versus the prior editions? There's a couple of things relevant to the conversation today. We have a new unified nominal shear capacity. I'll touch upon that briefly. There are new CLT shear wall requirements, which I'm not going to talk about. And then there's the new CLT diaphragm requirements, which I will talk about in depth. There is a free online version of the SPDWS available from awc.org, or I think you can purchase a hard copy or a PDF download version as well. But there's an online free version for you to reference for design if you don't have a purchase copy yet. Just as a reminder, though, this is a summary of what's in the design standards. I always like to say PowerPoint is not the code. If you're actually going to do the design, get the design standards and don't just rely on my presentation, which is more introductory and educational. So if you're going to do the design, get the actual code and make sure you read it and work through it. So what is in the new unified nominal shear capacity? If you've done conventional wood frame shear wall or diaphragm design in the past using the older versions of the SPDWS or the IBC or the UBC, there were tables in those versions where you had a capacity for wind and a different table, or in the one table, a different capacity for seismic. So the tables themselves gave you a wind design value and a seismic design value. And the wind design value was generally about 1.4 times higher than the seismic design value. With SPDWS 2021, these have been unified into a single nominal shear capacity. And then there are different adjustment factors for wind and seismic. This is, maybe very similar to what other materials have done, where you have a nominal value and you have maybe different phi factors or R factors depending upon the application for wind or seismic design. So SPDWS has kind of been modified to change to that same system of a single nominal shear capacity. And then other design values are derived from that. The changes, to start from a nominal design value and get to, say, a wind ASD value, divide by 2.0. To get to a seismic ASD value, you divide by 2.8. And if you look at 2.0 versus 2.8, it maintains that 1.4 increase factor for wind versus seismic. And then if you're doing LRFD design, use phi factors of 0.8 and 0.5. So everything, all your design values you might use are derived off of this nominal shear capacity using these relationships defined in the SPDWS. This is applicable for light frame shear walls or CLT diaphragms and everything in between. So CLT shear wall requirements, I'm not going to talk about them, but I am going to mention we have a good resource from Woodworks available that discusses the different options. Some people always ask, well, what's my R value for CLT shear walls? There really isn't one answer, because different detailing requirements can give you different R values. So if you follow certain rules, you can get an R value of 3, or different rules in R value of 4, or different rules in R value 1.5 or 2. So there's lots of options here. I'd be more than willing to talk about different options available for your project after this call and this meeting. But if you're interested, we have a resource that really talks through those available, that you can see the name of that in the URL online there. Okay, so now to the real meat of the conversation and the discussion point today. talking about the new CLT diaphragm requirements. You know, a typical floor assembly using CLT often looks like what we see here. We have CLT horizontal panel deck. Then we may have an acoustic mat or something similar on top of the CLT. And then there's the flooring on top of that, which may include kind of a cementitious layer like a concrete or lightweight concrete or a gypcrete, and then finished floor on top of that. Or if it's concrete, maybe a polished concrete floor. But that's a very typical assembly. Some projects have looked at that kind of cementitious layer and made it structural concrete and put the diaphragm system there. But it's kind of overkill and very challenging to detail and get that to work. It's much more efficient to use the CLT panel itself as the diaphragm. And now that we have a code recognized way to do that, that's the preferred way to handle those lateral forces through the horizontal diaphragm. As you can expect, the panel strength itself rarely governs, and what really controls the behavior is the strength of the connections between the panels and between the panels and the boundary elements around the panels themselves. So a lot of the requirements of the CLT diaphragms aren't about the CLT itself, but about the connections and the connections to boundary elements like chords and collectors and how all of that is checked. If you get the SPDWS 2021, open it up, go to section 4.5. There is less than 1 page of requirements for CLT diaphragms. They are very tricky 1 page of requirements, meaning it's very dense in terms of new concepts to learn to do CLT diaphragms. So we're going to tease those apart here and explain how you apply these into an actual design. The actual requirements themselves have been based upon and validated through multiple tests. AWC led a testing program, kind of what we see here. This is some pictures from their testing program where they really just kind of loaded up a CLT diaphragm using these topside, plywood splines, in this case, nailed to the panels themselves below. So in that kind of testing, you see a very rigid, kind of behavior of the panels. And then, really the connections is where all the interesting things are happening and what really limits the ultimate capacity, or the ultimate strength, I should say, of that diaphragm test. So the connections have very specific requirements. They're down in 4.5.4. I'll read this quickly, but then we'll step through what it means in more detail in the next several slides. The nominal shear capacity for dowel-type fastener connections used to transfer diaphragm shear forces between CLT panels and between CLT panels and diaphragm boundary elements shall be taken as 4.5 Z star. And it keeps going. You're like, oh man, that's thick. We're going to break it apart and talk about these different components and how you meet these. But first, I'm going to kind of give a picture of what a CLT diaphragm system might look like, what the different connections are in that system, and then what requirements apply to those connections and components. So if we have a simple rectangular diaphragm as shown here, maybe with shear walls on the outside, and a grid of panels resting on beams and girders resting on columns, you might have a typical panel in the middle that spans over multiple beams. In interior to that panel, you might have the panel resting on beams, which is really just a gravity connection and not really participating in the diaphragm behavior, much like you might see in a light frame wood diaphragm. In a kind of our engineering model, we kind of have a shear zone, which handles the shear forces, and then the kind of the bending of the diaphragm is handled by chords at the edges. And if you have just those limited shear walls at the ends and not full-length shear walls at the ends, then you might have a collector, which kind of collects the shear from the diaphragm and then puts it into the shear wall. If we zoom in kind of on the top left corner of that plan view and start to look at the different connections in that system, what we see are a series of shear connections. Connection A, shown in this little schematic, is kind of a typical panel-to-panel shear connection. Connection B would be kind of a panel-to-panel shear connection over a supporting beam or girder. Connection C on the left is kind of the panel to collector connection. And connection D here is the panel to the cord connection. So these are all shear connections taking shear forces into and out of the panels. But in this one particular corner panel, they might have 4 different connections at each edge. What those connections can look like, Alex has kind of already shown the connection on the left in a different view, bottom left, which is kind of just a plywood spline with nails or screws down into the CLT below. The views on the right are kind of showing the connections between CLT and framing below, whether that's a glulam beam or steel beam or a light frame wood wall with top chords. These are the kind of the shear connections at the edges of the panels. And that one paragraph that we started to read, has specific requirements on these connections. The requirements are the connections use dowel type fasteners and shear to transfer those shear forces, and those dowel type fasteners and shear, the nails or the screws, are controlled by yield modes 3S or modes 4 per the NDS calculations of the yield modes for capacity. Really, that is to ensure that those connections have that ductile behavior that Alex introduced. So these are the requirements to achieve that goal. The modes 3S and modes 4 are really the modes where you're relying on bending of the dowel, the screw or the nail, to achieve that's the controlling mechanism that limits the capacity of that connection. A lot of the other modes like modes 1 and modes 2 are relying on crushing of the wood fiber, and which is not as a ductile of a mechanism. So the requirements are to have these mode 3S and modes 4 control those capacities of those connections. So it's getting into the engineering and getting the design, but it makes sense when you think about the goals that are trying to be achieved. So what the different connections from panel to panel might look like. You have the top side surface spline on the left, whether it's nailed or screwed, and then there are the mechanical steel splines on the right, as shown in that example photo. And these are, all have the advantage of using the full width of the panel. The recessed splines on the left have the disadvantage of the additional CNC work required to make that spot for the spline to be recessed down into that connection. But they're all pretty efficient. The other approach, or that's more common, or not say more common, that is somewhat common, it's less common than the surface spline, is a half lap. Now here you cut out half the depth of each panel, and one side rests on top of the other side, and then you drive a screw through that full depth to tie those together. Excuse me. An advantage of this approach is it's a very strong and stiff connection. The disadvantage is you have to buy more panel because you have to buy that, those few inches twice. There is more CNC work required. But a big disadvantage of this one that they find they have to consider during erection is the sequencing. If you put one of these panels down and the other panel comes in next to it, it's either on top of it or beneath it. And you better hope you're applying the second one in with a crane is the one that sits on top, not the one that's underneath, or you have a real challenge getting that all to fit together. So how that is CNC'd should be really coordinated with the erection sequencing. And so that creates a real contingency during construction that the topside spline, whether it's a recessed plywood spline or the mechanical steel spline, doesn't have that sequencing challenging. So if you have a connection using the dowel type fasteners and shear, the nails or the screws, and you've calculated the capacity of that using the yield mode equations, and you have yields modes 3S or modes 4 could govern, that one paragraph of requirements that we looked at briefly says the nominal capacity of that shear connection is 4.5 Z star. And Z star is the reference lateral capacity Z of the NDS multiplied by all applicable factors except C sub D, KF, phi, lambda, they're all 1.0. What does that mean? What does that all mean? Basically, what we're starting from the reference design value Z, which is kind of like an unadjusted, long, short-term capacity of the fastener for ASD level loads, and then taking that to that nominal value. And then once we have a nominal value, we can use those reduction factors to go down to, the 2 or the 2.8, or the phi factors to go down to our ASD or LRFD strength, or ASD or LRFD wind or seismic load. So, but we need to have this nominal capacity, and this is how we get there. But what is this Z star? If you go to the NDS and say, what's my reference capacity Z, and how is that adjusted for the particular application for a connection, for a nail or a screw, for example, you have in table 11.3.1 all these adjustment factors. Usually they're mostly all 1, but they might not be because you have a moisture content in the timber over 19%, or it's a very hot application, or you have there's the different adjustment factors that are there. But the Z star really says, okay, let's ignore the ASD values, make those all 1. Let's ignore the LRFD values and make all those 1. And all those adjustment factors in the middle are the ones that we apply to Z to get Z star. So it's pretty straightforward. It's not quite the Z prime adjusted value because that's adjusted whether you're doing ASD or LRFD, but the Z star is this adjusted value where you ignore the ASD and LRFD factors and just apply the adjustment factors in the middle, which are usually 1.0 in most cases. For CLT diaphragms as well, the diaphragm factor is set to 1.0, so we don't get to adjust that as well. So we have our nominal capacity, then we go back to the adjustment factors that we've already, the reduction factors to get to our different design values. And if you run through the math, you get things like, 4.5 Z star divided by 2.8 for ASD seismic design. You get something that's really close to Z times C sub D of 1.6. So you're really, you're getting kind of to an answer you might expect if you didn't go through this route, but that's just for the ASD seismic design. You have different results for the different design conditions. So, okay, those were the shear connections. There's the other components of our diaphragm. So we have our shear in the panel themselves. We have our chords and collectors and the connections in the chords and collectors. What are these? These are really, the other components which aren't the shear connections. So it's the panels themselves, the spline, if you have one, transferring shear. If you're using the beam as a shear transfer mechanism between two elements, or you're using the beams or chords, beams or top plates in a wall as the chord or collector, these other requirements apply to these components in the diaphragm system. Those are found over here on the right-hand side of that one page of requirements. I'm not going to read through them, but just kind of give you an idea of what they are before you get there. It's interesting in that these components are designed to an amplified design force. Really, we want to make sure that shear connection using the fasteners, the screws and nails, controls the diaphragm system behavior. And to really make sure that what controls the diaphragm behavior, these other components are designed to amplified loads. That amplification factor starts at 2.0 by default, and then the requirement gives you exceptions where you can reduce that. So the first exception is you can use 1.5 for wood members resisting wind loads. So if you're doing a wind design, wind only design, then you can just start from 1.5. And then some of the chord splices have additional reductions. But really, all these other components are by default designed to an amplified load to make sure that shear connections control the diaphragm behavior. This was just an introduction. We have a short paper available called CLT Diaphragm Design for Wind and Seismic Resistance that kind of gives a little intro into this. But we also have a, it's like 80-page document, the CLT Diaphragm Design Guide, where we talk about these issues in great depth in terms of ductility, determining diaphragm flexibility, how would you calculate or estimate diaphragm deflections. This design guide also has pre-calculated connection capacities say based upon nailing nails in a plywood spline between connections. And then some subtle questions that come up like, well, if there's a force amplification factor in the SPDWS, how does that interact with other force amplification factors like the omega factor in ASC 7 that applies to collectors in higher seismic design categories? But probably most important, there are worked examples in this document where we take a design and we work through all the checks required to satisfy the requirements for that design example. And with that, I'm going to hand it back to Alex for some closing information, and I think we're going to have Q&A near the end.
Got it. All right. Thank you, Scott. Let me just share the screen again. So yeah, thank you, Scott, for going into depth about CLT diaphragms and just about spit widths. And with that, I would like to introduce to you guys the type of lateral force connectors that can resist those type of wind and seismic, which is our Titan Plate 1200 or our Titan Plate series. So our Titan Plate, let me just go here. Okay. There you go. Yeah. So our Titan Plate 1200 is similar to what Scott was mentioning, how we have to make sure that there's use metal connections to able to resist these lateral forces, and with our Titan Plate 1200, it's able to be used for this type of application. What's very unique about our product is you can use two type of fasteners. You have one, the LBA nails, which is our nails we sell here, and also our LBS screws. They're about the same size. There's two type of size you can use them for. You can use the smaller diameter one, which is about 5 millimeters. That's about like 3/16 of an inch, and then you have the LBS 7 millimeter diameter, which is about a 1/4 inch of diameter. As you can see, you can use them not only for CLT panels for floor to floor connection, but you can also use them for like CLT where you have the floor to the wall connection. So that's our longer version, the 1200. But we also have other smaller version as well, the Titan Plate 200. For very small, like maybe connecting two types of plywood. You also have the Titan Plate 300, where you can use it for wall-to-wall connection, CLT wall-to-wall connection, or maybe CLT wall to plywood. And those also is a different type of fastener as well. So you don't always have to use just nails. You can use them also our self-drilling LBS screws. That's one type of connection you can use for lateral forces. We also have a different, more unique connector called the slot. You can use this also for this deal for lateral forces as well. We see them being used for wall panels, floor panels, and many multi-story walls. Is just what it does is like a metal key you put into the CLT, and is able to handle the crushing forces of the lateral forces. And we also have some US value as well located on our website. And of course, this is something for maybe you want to use and in locations where you want to resist some sort of lateral high shear forces. However, one thing to know is that maybe you're in an area where like maybe the building code you need to get some special approval. So that's why there's us, the consultants here, to provide some guidance in order to determine how to go about handling these type of requests, and like maybe you need some special help from us. So we're here to help. There's resistant forces not only for the U.S. design for the U.S. but also for Canada and for Europe as well. So If you have some projects in Canada, we have a technical data sheet for Canada as well. Um, but speaking of back to the Titan plate, one thing you also have to consider for these type of line connection is also maybe you might have to deal with like CLT floor panels, but also finding a way to maybe for fire protection. As you can see, metal is very conductive. You can feel it. When it's cold outside, it gets cold. When it's hot, it gets hot. And then when there's a fire, well, you have metal on timber, and um, it runs into an issue where maybe fire can get into the wood, and we don't want that to happen. A lot of time, with a lot of fire rated connectors, they're usually hidden, but with the with the Titan plate being exposed, we try to come up with a way. Maybe there's a way to provide some guidance for protecting the metal and also protecting the wood. So we have done some fire testing. Um, the first the first couple of tire testing involve very simple like timber connection, just incline screws connect like butt joints, CLT connection. We had did some spline. We also did some half laps, but then we came to our third fire test campaign where we use our Titan Plate 1200 with a one of our membranes called the Defense Adhesive stripe. This is very as one of those one of our transparent membranes where you can use them to apply it on top of a COT floor. It's a way to protect the wood from from the site, from rain if ever to come. But we also figured out that you can also use this as well to protect it from fire as well. So this is just the schematic of what we did. What we did was we used about a very one put the defense adhesive on top of this metal connector, and then after what we put it through a um, fire oven, and what ended up happening was that it was able to resist, give us a grade of EI 90. This is for more for this is a different kind of standard. But what it means is that this type of connector was able to resist about 90 minutes of fire before the connection fell. And so, as you can see, even with this Titan plate being metal and being very conductive, it was able to resist uh, about 90 minutes of fire, which is that's something to consider. Maybe you want to make sure that when it comes to fire protection, you can use there's a way to cover up our spline plates, or even just use our defense adhesive um, as well. One good thing about our membranes is that it's transparent, so you can see where the failure is happening, or maybe you can see the wood as well, which is important because you want to make sure when it comes to inspection, you want to make sure that you have an idea of where maybe water got into, or maybe there's something you have to replace. You want to be able to see the wood, so um, that's something just about our defense adhesive. You can learn more about it later on our future webinars. Where we talk about more about membranes, but this just to give you guys an understanding of what how much other products we have besides just fasteners and connectors. But with the Titan Plate 1200, um, be able to get some revision. We always also do some calculation as well to determine the capacity of our line connector, and following the spit widths guidance, as long with some extra help, we were able to see figure out about what's the capacity of our 10 plate 1200 depending on different spacing. So maybe, for example, you want a 2-inch spacing. Obviously, there are much more screws you're going to use, but the more spacing you have, the less the resistance gets. But just following the seismic and wind from split widths, we're able to calculate um, the capacity according to according to the SPITS with 2021 codes. One thing to also note is that depending on the building code, maybe it depends on where you're using it. Like it could be in a state where maybe the building code is not up to date, like so the more like 2024. The calculations are different, but this is for this any states that are using the building code 2024. And so stay tuned for the technical data sheet to be published for the Titan fleet. And you will able to see the resistance of our spline connectors. So yeah, so that's all we have for today. We're just about to meet our 1 hour mark. If there's any questions, please send it to the Q&A. Well, other than that, thank you for being here. And thank you also to Scott as well for being here with us. So, yeah.
Perfect. Can you hear me? Yeah, awesome. Yeah, thank you, Alex and Scott, for the presentation today. As of right now, I don't see any questions in the chat, but if anybody does have any questions, please feel free to send them either directly to Scott or to eng.na at rothoblaas.com, and we can get the answers that you're looking for, whether that question happens in an hour, a day, a week, or even a month from now. So that's why we're here. And we always look forward to having you join us for our webinars. We do have a few more webinars planned throughout this month, and you can find the registrations and the links for that on our Eventbrite the same way that you found this one. So with that, enjoy your Wednesday.
All right. Thank you, Chris. Thank you, Alex.